Following on from the previous video, we got to this stage here. We got to this stage here. We got to this stage here. We were trying to find out what happens around this region here. But rather than looking at this region here when t equals 2 pi, let's look at it when t equals 0. It's easier to analyze it when we look at when t equals 0 rather than when t equals 2 pi. This region here will act the same as around here. So let's look at it when t equals 0. It's easier to analyze it because we're going to use Taylor approximation. So remember from the previous video, the position vector is given by this. So we can translate it as x is given by this, y is given by this. And we can use Taylor approximation for when t is very, very small. We can replace this with Taylor approximation. So remember in the past we would do this. If you look at sine looks like this. Sine looks like this. But when t is small, we can just use the line y equals x. We can just use the line y equals x to approximate sine of x around this region. So I'm expecting you to understand the Taylor approximation. So around this region here, we can just simply write sine of x is approximately x. So around this region here, we can just put t into this block here, and then remember we can approximate cos t. We can approximate cos t as this. Hang on. We can approximate cos t. So cos looks like this. The cos graph looks like this. But around when t equals 0, near t equals 0, we can just approximate it with the line y equals 1. So we can approximate cos of x is approximately 1. So we can just use it as this, or you can use this formula here. We've done this before, so I'm expecting you to know this. I'm expecting you to know that when t is small, we can just replace sine of t as t. When t is small, we can just replace cos of x as the number 1. So we can put this into here, and this into here. So when t is small, when t is very small, when t is very, very small, we can actually try and understand what happens when t is very, very small. That's why we're using Taylor approximation. So, but the thing is, when you put t into here, you're going to get t minus t, which tells you nothing. And then when you put 1 into here, it's going to tell you nothing because our accuracy here is not good enough. We are only using the first. We're only using the first term here, but if you want to, we need to increase the accuracy. So rather than just looking at the first term, let's look at all these terms here. Let's look at the first 4 terms. If you want to increase the accuracy even more, you can even take it further. But let's just increase the accuracy. So rather than just using sine of t equals t and cos of t equals 1, let's increase the accuracy by looking at more terms. So now we're going to look at more terms. So let's approximate sine. Let's increase the accuracy here. So sine, if you want to approximate sine when t is small, look at it when so this will be sine of 0. Differentiate sine, that will be cos, and then evaluate it at 0. That's why you've got this 0 here, and then you've got your t here. And then look at the second derivative. The second derivative will be minus sine, and then evaluate it at 0. So that would be sine of 0. And then you've got this thing here, which is this thing here. Now let's look at it. Let's look at the fourth term. So the fourth term would be you taking the third derivative, which will be cos, and then evaluate it as 0. Evaluate it as 0. So this block here will be this, and then you've got this thing here, which would be this. So sine of t. Well, if you tidy this up, sine of 0 will be 0. Will be 0. So this thing here disappears. Cos of 0 will be 1. So that's why you've got this t here. and then this thing here would be 0, so the whole thing here would disappear, and then this thing here would be 1, so you've got minus t squared over 6. You've got minus t squared over 6. So sine of t, we can replace sine of t as this block here. We've increased the accuracy now. So this is a better approximation than simply sine of t, which was what we used earlier. So increase the accuracy and do the same for cos of t. If you increase the accuracy, you can replace cos of t with this. So rather than using cos of t equals 1, use this. This is more accurate. Okay, so sine of t is given by this, cos of t is given by this. So we can now put this into here, and then we can put this into here. So this whole thing here will then become this. Will then become this. So if you tidy this thing up, that will then give you this. Tidy this thing here, that will give you this. So looking at the path of the cycloid, hang on. Looking at this bit here, remember we are trying to analyze this, but we are really considering when t equals 0. So I'm just going to talk about this bit here to illustrate this point here. So if you zoom into this bit here, it will look like this. It will look like this. It will look like this. So remember, x in the x direction is given by this, in the y direction is given by this. So if you look at this thing here, this is like a gradient. If you look at the gradient of this thing here, the gradient of something would be the up and down y divided by the across, this thing here. So if we get the up and down, which is y divided by x, so that would be this thing here. This is y here, divided by x here, which is given by this. Tidy this up. So the gradient y divided by x, which in our case represents a gradient of this thing here, is given by this. So hang on, bear with me. So the gradient. So if you look at y divided by x, that really represents a gradient. If you get the up and down, divided by the cross, that will then give you the gradient. Well, the gradient is given by this. So when t is near 0, when t is approximately 0, when t is near 0, look what happens here. When t is near 0, so imagine this number to be 0.00037 here. This whole number here would be massive. So you know the gradient would be really high, really steep. So it won't be this scenario here, because if you look at this here, the gradient is near flat. It won't be this one here. It won't be this one here, because the gradient here is kind of flat here. And it won't actually be this one here, because let's just say the angle here. Let's just say the angle here is 70 degrees. Let's just say that. Then this thing here wouldn't be real. Well, this thing here is really steep. It's telling you it's really steep. So the steepness should be like this. It shouldn't be at a certain angle. It would be really steep. So the only scenario it could be is this one here, where around here it's really steep. Around this region here, it's really steep. So the point I'm trying to make is that if you look at the gradient, if you look at the ratio, the gradient tells you that when t is near 0, the gradient will be really steep. The gradient will be really steep. So it can only be this scenario here, not this one, and not this one here. So hang on. So if you we're trying to understand what's happening around this region. If you zoom into this bit here, it will look something like this. It will look something like this. But if you zoom in even further, the steepness here will be, well, the gradient will be near. It will be really steep, basically. Okay. I hope you understand that.